Friends, welcome to the Essentials of Inorganic Chemistry. As always, let me first seek the blessings and recite a verse before I begin the class. By the infallible compassion of Lord Chandramoleshwar, may all the learners of chemistry get a great success in all their noble endeavors. Here comes the 11th verse from the second chapter of Rudrashtadhyayi. ब्राह्मणोऽस्य मुखमासीद्बाहुराजन्याः क्रतः उरूददस्य यद्वैश्याः पदभ्याद्घुशूद्रो अजायत. So we are discussing a very important topic in general as well as in organic chemistry, optical isomerism. This is the 11th talk in the series, and today we will be discussing optical isomerism in octahedral complexes with general formula like MAA thrice, MAB thrice, and few others. The prerequisites of this lecture are same as the previous ones, but I would like to always repeat it. The basic knowledge of coordination chemistry, basic knowledge of elements of symmetry, the power of imagination, and today we will be answering a very interesting question. Is it true that the optical isomerism in complexes of type MAA3 or MAB3 is best seen at 12 o'clock, 20 minutes and 40 seconds? Let us check it. So, first we take the complex of the type MAA thrice, and here I am showing you a dial of a clock, and here the time today is, you can see, 12 o'clock, 20 minutes, 40 seconds. This is also known as Newman projection. This is very much discussed in organic chemistry. I will show you an example of Newman projection for a molecule like ethane. Friends, this is your ethane molecule. If you already studied this at some level, then it would perhaps appear very elementary to you. But otherwise, just see. We would rotate it a bit, and then see what I have done is I have tried to maintain the time as I showed you in the dial. This your carbon is at the center, and see, I have already told you about the color scheme that I am maintaining in my entire presentation. I have a set of 7 colors: pure, violet, indigo, blue, green, yellow, orange and red. And in all my presentations you will see that the red color represents that the atoms are coming out of the plane, whereas the violet or the blue colors, they indicate that the atoms are behind the plane. So you have 3 red hydrogen atoms that are coming out of the plane and 3 blue colored hydrogen atoms that are going inside the plane. This is your ethane in its staggered form. And see, the first hydrogen atom is at 12 o'clock, the second one is at 4 o'clock, that is 20 minutes, and then the third one is at between 7 and 8, that is 40 minutes or 40 seconds. Just see, if I rotate it, you will understand that this is clearly your ethane. So with this brief introduction, I would like to explain you that how you can use this Newman projection or a clock dial in understanding the optical isomerism in your MAA3 type of complexes. Let us take this one. Sir, yes, I got it. So this is your complex. The formula of this complex is MEN thrice. You can see that the ligands are 3 in number, and they are NH2, CH2, CH2, NH2. This is the first set of ligands, this is the second one, and this is the third set. Now, I want to decide whether the arrangement of the ligands that is shown in this figure is delta or lambda. That is, whether this complex is having the absolute configuration C or A, sometimes also called delta or lambda. Delta represents the dextro, that is the right or the clockwise, and lambda represents levo, that is the left or the anti-clockwise. And what we do is we will try to see the direction of connection of the front atoms like this, you have N13 in the front, you have N4 in the front, and N9 in the front. How it is connected to the backside atom? So see, the first one N13 is connected to the N12. Now going to N12 from N13 this way, it is a clockwise movement. Now let us take it for N4. N4 is getting connected to N5, and this movement is also clockwise. See, clockwise or right-handedness. Then see the N9. N9 is getting connected to N8, and this is also clockwise. Once again, I will repeat. What we do is we arrange the complex in such a way, which I have already shown you, like a dial of a clock, that the timing appears like 12, 20, 40. 12 o'clock, 20 minutes and 40 seconds. So these three atoms, this 12, this 20 and 40, these are occupying the front, whereas the remaining three atoms colored in green, they are occupying the back, and these are in staggered form. Now what we do is we see that how the front atom is connected to the back atom. So the first front atom N13 is connected to N12, and this is going clockwise. So it is delta or C. Then the other front atom N4 is getting connected to N5, that is also going clockwise. We are moving clockwise. Then N9 is getting connected to N8, that is also clockwise. So this one clearly is your C or delta isomer. Now let us see how is the lambda isomer. This one. Here what happens, again we have arranged the atoms in such a way that the red atoms, the red colored atoms are occupying the front, and the green colored atoms are occupying the back. Now try to connect front to back. See what happens over here is N13 is connected to N12, but going to N12 from N13 requires a anti-clockwise movement. Then go to the second front atom N9. N9 is connected to N8. Going from N9 to N8 requires an anti-clockwise movement. And in the same way, the third front atom is N4. Again, it is connected to N5. And moving from N4 to N5 requires an anti-clockwise movement. And therefore, this is going to be your lambda isomer. I hope this is clear to you. And the best way to view the optical isomerism, and particularly MAA thrice or MAB thrice type of complexes, is particularly this, that you use a Newman projection kind of orientation, and then you will be easily able to see the left-handedness or the right-handedness, that is the absolute configuration of your isomer. Now we come to MAB3. This time, okay, let me just show you and then I will explain you. We are having glycine as the ligand, NH2CH2 C double bond OH, and the formula of the complex is triglycerine chromate or chromium. This complex, first of all, in the geometrical isomerism point of view, you will understand that this is a meridional isomer, because number one, see, the complex is of the type MAB. Now AB represents a bidentate ligand with two different ends. Here you have, in the glycine, you have one end occupied by nitrogen and the other end occupied by oxygen. So in MAB3 type of complexes, if you refer to my lectures on geometrical isomerism, you will understand that these type of complexes can show FAC and MAR, that is spatial and meridional type of isomerism, which are also called cis and trans. So the meridional isomerism does not allow you to make a triangle on the face. So this is the three oxygen atoms do not make a triangle, instead they make a V. And in the same way, the three nitrogen atoms also do not make a triangle on the face, they make an N. So this is clearly your trans isomer, because here also you will be able to see that the two oxygens are occupying positions opposite to each other. Now this trans isomer is capable of showing optical isomerism also. So this trans isomer can further exist in two different arrangements. Let us see the first one. This is the first arrangement, and again we are applying the Newman projection kind of thing. So you have at 12 o'clock your nitrogen, oxygen, and yet another oxygen, and behind you have nitrogen, this green, this oxygen, and this green nitrogen. Now see how this 12 o'clock nitrogen is getting connected. It is getting connected to this oxygen, and for going from this nitrogen to oxygen, what happens? We are taking a clockwise move. Then let us come to this oxygen. This oxygen is getting connected to this nitrogen on the back side. For going from this oxygen to nitrogen, you have to again take a clockwise move. Right? This oxygen to this nitrogen, again a clockwise move. So this is a C or a delta isomer of the FEC isomer, MER isomer of CrGly thrice. Now I will show you the lambda isomer for the meridional chromium triglycinate complex. See this. Now you have again the three red colored atoms on the dial, 12 o'clock, 4 o'clock and 40 seconds or whatever. Now see how these are connected. This is connected to this. But for going from this nitrogen to this oxygen, what happens? You have to move anti-clockwise and come over here. This nitrogen is connected to this oxygen, and again for going from this nitrogen to this oxygen, you have to move anti-clockwise. The same is the story over here. The red oxygen, and for going from red to green, you have to make a anti-clockwise movement. And again, this isomer is a lambda isomer, because lambda or anti-clockwise isomer. But see friends, this again is a meridional isomer, because in the geometrical isomerism point of view, the three oxygens, they cannot make a triangle, they simply make a V kind of shape. In the same way, the three nitrogens, see, they also cannot make the triangle, they make a V kind of shape. So this is a meridional isomer, and this is lambda kind of meridional isomer of chromium triglycinate complex. Now I will show you the FEC or the facial kind of isomer for our chromium triglycinate complex. So how do we see that? Just take a look at the three oxygens, the three oxygen atoms and the three other nitrogen atoms. These three oxygens make a triangle, very clear triangle. In the same way, these three nitrogens will also make a triangle, and therefore this is a FEC isomer. Now this FEC isomer can also exhibit optical isomerism. See how? We have again arranged it in a dial kind of situation. The front, just keep track on the red colored atoms, and then you will understand. The red ones or the orange ones are in the front and the green ones are in the back. See the connection between the red and the green. In which direction it is going? Anti-clockwise. Here also the red one this way, anti-clockwise. So then this one going from the front to back, what happens? Red to green, you have to move anti-clockwise. So this one is again your lambda isomer. Now I hope you will understand that if you can make a lambda isomer, you can also make a delta isomer. Let us see how I can simply convert. If some of you are using this kind of software, then I will show you how simply you can convert this into this lambda isomer into delta isomer. What I am doing is I will invert through origin. I have inverted this through origin, and see the structure has changed. Now see, red to green, front to back, you are moving clockwise. Again, red to green, front to back, you are moving clockwise. Red to green, front to back, again you are moving clockwise. So this is now your lambda isomer. That is the right-handed or the C isomer. So that was something about the glycinate example. Now what I will do is I will show you an example of some EDTA complex. First of all, EDTA is ethylene diamine tetra acetic acid, and it is a hexadentate ligand, very important compound in chemistry. See the structure of this. This is your EDTA. It is hexadentate. The coordinating atoms are 6 in number. 2 of them are nitrogen. You can see this nitrogen and the other nitrogen. See, EDTA means ethylene diamine tetraacetic acid. So you have ethylene CH2, and your diamine this N and this N, and then tetraacetic acid. Each of the nitrogen is connected to acetic acid, CH3 C double bond O and O, and the other one CH3 C double bond O and O, and the other nitrogen is also connected to 2 acetic acid groups, and this oxygen. So one oxygen from each of the acetic acid group also acts as a coordinating atom. So EDTA in all makes a hexadentate ligand. The geometry of the EDTA complex is going to be octahedral. I will show you how. This is your EDTA complex. I will show you the geometry later on. First we will take how to distinguish the lambda and delta isomers of your PDTA complex. So this time, this is a little bit distorted structure, so I will not be able to show you exactly on the dial kind of system. But again, what I have done is I have kept 3 oxygens on the front side, and the remaining two nitrogens and 1 oxygen on the back side, not exactly staggered, but slightly staggered. What I am doing is I am trying to see the direction of movement while connecting the front side with the back side. The first oxygen, I am moving from oxygen to nitrogen, and this is a clockwise movement. Then the second oxygen, I am moving from oxygen to nitrogen, and this is again clockwise. And this time, this is connected, this oxygen is connected again to the same nitrogen, but this time I have to move anti-clockwise. But 2 clockwise and 1 anti-clockwise, therefore I will call it dextro or the delta isomer. The other one, when I take, what happens is, see, the first one, I am moving from this oxygen to nitrogen. And how do I move? Clockwise, right? This is clockwise direction. Then the second oxygen, this time it is connected to this nitrogen, so I have to move anti-clockwise. So this is your anti-clockwise movement. 1 clockwise, 1 anti-clockwise. Now come over here. This nitrogen is connected to, this oxygen is connected to this nitrogen. So I have to again move, oxygen to nitrogen is moving anti-clockwise. So 2 anti-clockwise movements. Therefore this is going to be my lambda isomer. This is a little bit complicated structure, so I am attempting one more thing along with showing you these structures. I will show you a video of 1 minute, which will perhaps enable your better understanding on the optical isomerism in your metal-EDTA complex. Just take a look at this video. This is a 1 minute video. On the left hand side you have delta isomer of the cobalt-EDTA complex, and on the right hand side you have the lambda isomer of the cobalt-EDTA complex. Friends, I have been putting up a lot of efforts in preparing these videos for you, and as you all know, this is an entirely free channel. So what is my reward? My reward is your support. And what is your support? Your support is in terms of number of views, in terms of number of comments that you put, in terms of the number of demands and requests that you put regarding the different topics that you want to learn on. And your support is also to increase the number of subscribers on this channel. So I very earnestly request you that please ask your friends to take maximum benefit of this channel, so that I get encouraged and I keep on posting more videos for you. So as that was something about the optical isomerism in complexes of type NAA thrice and AB thrice and EDTA. Most of the times I do keep informed you about the topic of the upcoming lecture, but this time I am not sure on what topic I am going to conduct the next lecture. I have received a few demands. One was about the reaction mechanism in octahedral complexes, that was about explaining SN1 and SN2 mechanism, and somebody also requested me to put the part 2 of the Walsh diagram, and one of my subscribers also requested me to elaborate on the Huckel's method. As far as the Huckel's method is concerned, I have already elaborated. Please see the playlist and you will be able to find the entire treatment on the allyl system. About the Walsh diagram, I will be doing it as soon as possible, but I am not sure that whether it is coming up or not, and therefore I have not shown it in this slide. So thank you.